I think to open our event, let me talk first of the agenda, and then I'd like to ask the audience a question. But for our agenda, we're going to talk a little bit about graphs as a launchpad of a variety of different technologies, where we're seeing them continuously, especially in large telco organizations. I'll go through to make this particular event different from the network and IT operations event we did a couple of weeks ago. I'm going to focus a lot of time on why the Neo4j graph is a good choice versus other types of data storage or processing alternatives. And then we'll talk a bunch about a variety of case studies of real telecommunications companies using us out there in the wild. So to open, Corey, let's fire up the poll. And our question that we have to start out with is, please give us a quick question. Are you planning on attending the Graph Connect conference that we're holding? We've got one coming up in about 2 weeks in May. In London, and then we have another one scheduled for New York City in late October. The date will be is still TBD, but you can look for that on the Graph Connect website as well as the Neo4j website when it comes up. But we'd love to certainly have you join us there. So just give us a yes or no or maybe on this particular poll, and we'll give it a couple more minutes, or not even minutes, a couple of seconds. Okay, we've got about half, so just as you guys hear the results, about half said maybe I'll go to New York, and the others said no, I can't. So that's great, thank you very much. Okay, so let's roll back to our particular agenda here, and let's get into a lot of the reasons why we're so excited about bringing graph technology to you. It really is that we've seen, and I'm sure you've seen out there as well, graphs are really transformative in the situation of being able to highlight, transformative in a business, being able to highlight relationships in information and data, oftentimes connecting different people with networks, with applications, etc. But it's been transformative in specific industries, internet-based industries. You can see how Google's transformed the world of search, LinkedIn has transformed the world of business communication and job seeking, and PayPal is transforming the banking and money and payment industry. And all of these are great examples of how graph technology itself is making a big difference in those business models. The common themes that you'll see here are just the connections themselves in connections between, as I said, different systems, different devices, different the relationships among people, the relationships among people and their particular roles in business, etc. All of those are drivers for why graph is so popular. So when we look at this particular topic and using graph technology in the telecommunications industry, our original webinar that we did, this is part of a series of webinars we're doing on infrastructure, network, and IT operations. But this particular, this is our middle event. I wanted to also highlight, beyond network management, the opportunities or the situations where we see application good use cases for the graph technology are all over the place, whether it's the IT infrastructure, whether it's the payment processing and fraud detection, whether it's creating real-time recommendations in the call center, whether it's understanding all of your different customer touch points, especially if you offer multiple services to those customers, like TV, internet, and telecommunications. Graph is a great vehicle for dynamic pricing applications. It's great for the underpinnings of any type of artificial intelligence application or any type of IoT type application in connecting your your specific devices to your gateway devices, and then mapping gateways back to particular business functions. That's a great application. Managing identity and access management is another example. We have a case study coming up on that, as well as your delivery chain, and your specific external delivery network. So an example here of all of the different models of graph that we could find when we just searched on images of network topology. We really look at that as this is an example of a variety of ways to represent a particular network. And if we zoom in on one picture, we look at a cellular network, a Wi-Fi network, and a WiMAX network that are all hooked up in a particular telco backbone, and you can see where there's perhaps a poor connection event happening in within the network. Well, all of this really turns into very, very nicely a graph-based kind of model where we can see the relationships not only from each access point or gateway, but all the way out to how that operates all the way up through the mesh router, gateways of that, etc. These are all great graph kinds of representations and problems. And one of the reasons why that turns out so well is, of course, because when we think about how we want to lay out the network, what we want to run in the network, oftentimes we whiteboard this up as an example of, in this particular case, we're looking at what's the corporate relationships between Acme and Jupiter Technology, and how does that map out. Again, that physical model that you might draw on a whiteboard, that logical model, excuse me, on the whiteboard really does become how you want to represent that information in a physical model and stored and accessed as a graph. Here you can see we've got the different services that are available to Jupiter Technology. There's different devices that they might be carrying and subscribe to particular service levels, etc. Those are a really great example of how that idea or that particular logical model that you may end up mapping out does lend itself really effectively to becoming a graph within which we can store, navigate, and use as real information in the system. So it's really easily understood. It's easy to evolve. Connections between these different nodes is really easy to manipulate and maintain, and then provide a really rich set of information or properties against these that you may not have thought of before. So when we do comparisons about why is it the graph is so important, and why can't I handle something like a graph model using a relational database? And I think the illustration there on the right-hand side is very effective here in showing that the relationships between tables is as joining that information together is really what we end up modeling inside of the graph. But it's not a first-class citizen in terms of the RDBMS model. It doesn't have any of the nuances or the ability to declare properties against a relationship without adding a huge amount of complexity, and a full external join table, perhaps between two different entities to describe what their relationship is. So the representation is awkward, but then when you start to use that representation from a relational database, the larger your set of relationships or your network grows, the more likely that your performance of that application that's using that RDBMS is going to slow down, because the more joins, of course, you have to execute, the more resources you use, the slower response of your queries, and ultimately our customers had often run into situations where they hit what we call the join bomb, where the system just basically runs out of memory and dies because it can't handle the complexity of 10s, 20s, 30s types of joins in order to get information back from a particular query. So, and then changing this model, a relational model, is very cumbersome versus simply adding a new connection or a new relationship or a new node in the graph model. So really inappropriate ultimately for that, for real-time types of applications. So as I was talking about earlier, there's a variety of situations inside a telco where graphs are appropriate. So organizationally, mapping out perhaps the different employees. You have your service technicians. In many cases, you might have your indoor service technicians and your outdoor service technicians. So those folks organizationally, where they roll up, what locale they happen to be in, what coverage areas they happen to be located, what skills and expertise each particular technician might happen to have. All of those kind of relationships can be really easily modeled using the graph, and then creating an application that identifies who's the right service technician to solve a particular customer problem in the most appropriate timing. That whole exercise can be easily, as I said, mapped in a graph. And we actually have telco customers who are cable providers who are doing exactly that kind of graph inside their organization. And we can look at identity and access management for customers. That's a really great situation to use a graph. You have your customers who are on their devices. They might be logging into their, as I said, the cable box, their telephone, their computer. Perhaps there's a internet connectivity to their car. Those kind of items is mapping all of those back to a particular user or a particular user ID, and then what the privileges are for that user to and what level of service they happen to be subscribed to. So perhaps one customer has a valid, high throughput data plan so that their car can indeed be processing videos for the kids in the back seat. That whole exercise is well modeled in this identity and access management kind of use case. And then the other great one is the IT operations at very, very large scale. The graph is a great way to help reduce that complexity in the environment. So let's talk about a couple of real, a situational use case of how you might deploy the graph technology inside the organization. And you'll see I keep switching the variety of use cases we're laying in, because every one of these is appropriate for a large telecommunications company. This particular picture happens to be the model of a server in the center where the halo is, and all of the different port connections coming into that server from a number of different IP addresses. And so this might help model a network traffic or suspicious activity happening against that server, perhaps a denial of service attack, that kind of thing. So what I'm going to look at here is I'm going to map out an environment where the network itself is handling financial transactions, and so perhaps that's the billing network. And what you might want to be monitoring for is suspicious activity on the billing network. So we'll say the transactions themselves are drawn and operating through the relational database. The data science team is trying to look at behavior patterns within that information. So using the RDBMS is great for your discrete analysis here, but it's not as good for providing that holistic view of perhaps what other devices has that customer got, what other activities are they performing against other services. That holistic view is less easily represented using the RDBMS. So then we switch to using a data lake and try and centralize all that information and shift the data science team to looking in a much larger environment. So that's, again, great for aggregating perhaps data from the ISP side of the house, from the content provider side of the house, the customer service provider of the house. Great for identifying those kind of things. And again, analytic workloads that operate in batch or in slow time are very, very good for the operating in the data lake. But you still don't have that holistic view. You still don't have a perspective into what's happening operationally right now, and the processing time takes quite a while. So what I'm going to end up introducing in the green there is the graph cluster. Let's call that Neo4j. And what can you do there is load in the relevant relationship information as a model of the graph, and then apply that and watch that as it's operating against the real-time information, right? It will sense the transaction stream, and then if there's anomalous activity happening in the transaction stream, take appropriate action there. So respond with an alert, a notification, a temporary service shutdown. Things of that nature are what the graph database can help process, and it can help lead that data science team to identify more effective patterns of odd behavior or anomalous behavior because of the visual nature of the graph itself. So here's a great kind of example of when you might want to examine what's happening in the graph and use that to identify what your next set of perhaps predictive or anomaly detecting models are going to be. So now we'll look at, I've given you the foundation for where we might apply the graph and identify situations where navigating relationships is really important, or maintaining connections amongst disparate systems is the ideal goal. So we'll look at, so what is the right technology when you're trying to do that? So we evaluate a lot of different storage technologies kind of along a spectrum. And this spectrum from the left-hand side is dealing with, we'll say, discrete data elements, log files, and a storage of years and years and years worth of log files, data that's minimally connected and oftentimes useful for that big batch operation of analytics. You might have your relational storage system in the middle that was kind of the trigger for going on large volume and veracity on the left-hand side, and on the right-hand side using a graph, triggering the need for managing connected data and managing the relationships among the data, regardless of what silo that data may originate from. The graph is a much better representation of that kind of information. So graph databases themselves handle data relationships, as we've mentioned. The development benefit is that it's a highly visual and intuitive kind of vehicle. We're starting to see, and we often recommend to customers that graphs themselves are really easy to learn, but they're hard to master. And so they still take the investment of time and experience, that 10,000 hours, if you will, to become a solid graph master in understanding exactly how to build and deploy a really high performance kind of application. But that's where the experience of an organization like ourselves comes into play. So when we evaluate that, if we look at just the deltas between the relational database and the graph environment, what's going to stump up the relational database system? And really what we find is the queries themselves. If you're looking at or trying to navigate about a graph, a single query can touch a lot of nodes and touch a lot of data. And if you're doing that on the relational side, then you're doing lots of index lookups and lots of joins. And that exercise is resource intensive and expensive. The other thing that can happen in graph type queries is they can take non-sequential or odd paths through the data. So the pathing exercise, or the number, oftentimes we refer to this as the number of hops, right? How many traversals do you need to take in order to understand and retrieve the exact amount of data that you want? That activity, again, could be very resource intensive if you're doing lots of joins. But if you're doing graph, then that activity is actually because of the nature of a native graph system, you can actually predict, the cost of every hop, and therefore if you're traversing 10,000 hops, you know exactly what the resources are going to be required to do that. And it grows in a very predictive way because each hop is sequential and not necessarily linear in terms of its resource expense. That's great, especially when you're trying to do real-time activities. And that's great when you want to make sure that the results you're bringing back is indeed both reliable and consistent. The core technology behind all of that, right? What's the thing that makes that work so well is this concept of index-free adjacency. We're not using indexes with from a node or any one of those dots. We store the data and its connections as we write it to our own storage container, and so that pink dot in the middle knows the other nodes to which it's connected and knows what kind of relationships it has with those other nodes, and therefore it can traverse very, very rapidly simply as a pointer to its related nodes. And once the related node receives that traversal hop, it behaves the same way. So the costing of doing all of that in terms of resources is very, very predictable and very, very fast because you're just chasing pointers. There's another degree of complexity anomaly or consideration when you're trying to move from a relational situation to a graph situation. Let's look at this query here. This query says, find me in an organizational hierarchy, find me all the direct reports, right, and how many people they manage, and navigate 3 levels down. So the query that we're executing on the left-hand side has a number of joins and subselections from a variety of systems in order to accumulate all of that information. Whereas the same query on the right-hand side, using Cypher, the Cypher programming language, which is the natural language there, or the SQL for graph, you can see it only has 3 lines or 4 lines, where you can say, match, where the boss manages himself, and then 3 levels down, and report, and the boss's name is John Doe, so report back both the names of the subordinates and count them. And there we are, and that's what it takes to execute that kind of query. Really, really simple to read, really simple to understand, versus the SQL statement on the left-hand side. So for developers or those that are responsible for these queries, you spend less time writing them. They're more legible, and they're much more they're cleaner to debug, and significantly easier to read, not only for yourselves but also when you're communicating perhaps with other members of the team, or even other external members of the organization. Perhaps they don't know programming languages at all, but they can still figure out what's going on here. And that net result is, from a performance standpoint, it could be thousands of times faster than what you would see with a relational system. And as your data environment grows, and big telco environments start large anyway, that's really important that you have a nice consistent performance chart that tells you what your response times are going to be as you grow out the size of your graph. So now we'll look at, okay, so relational may not be the appropriate set of technology to use. Let's go other NoSQL systems. We'll look at key value pairs. That's just like looking at indexes all day long. Or perhaps look at the columnar family of data, where the columns themselves are much easier to traverse than rows in order to find particular pieces of data. Or we'll look at documents, because documents are more like what you find on the internet. And in each one of these cases, you'll notice that identifying relationships in the data doesn't really exist here. There's not any real structures to model, and therefore there's no opportunity to store relationship information. There's very few query constructs to support those data relationships, and you still have to, in order to find and identify the relationships, you still need that old join logic. So you're going to run into the same kind of situations as we ran into on the relational side. And then lastly, Many of these kinds of technologies gain their scalability through horizontally scaling across a number of inexpensive nodes of hardware, inexpensive instances of hardware in the cloud. And in order to scale that way, they support an eventual consistency model. And the bummer here is that when you're trying to store graph information in an eventually consistent manner, well, you really run the risk of your NoSQL kind of system becoming, eventually inconsistent and eventually corrupt over time. So you might have situations where as the node and relationship are getting written to another server in the environment, you might get a ghost vertex, right? That's a vertex is a node with no relationships. You might get odd or stale indexes, so you can't find the node that you're looking for. You might get half edges, which are unconnected relationships; they go nowhere. Or you might get unit-directed edges. So what that means is there's a relationship and it has no nodes connected to it. So all of those are particular areas where you want to ensure that your data is indeed maintained to the highest degrees of integrity. And a Neo4j type system does support ACID consistency, and therefore the integrity as data is moved about its cluster is also maintained at that ACID level. We don't complete a transaction unless it's fully completed or not. So before we kind of move into our next section of different case studies, the core element here, the graph database, is really great at connected data, whether that's your network data, whether that's your employee data, your customer data, your external topology data, your IoT data that you might be thinking about. All of those have relationships amongst itself, as well as relationships amongst different levels there. So look for an enterprise-grade native graph database like Neo4j to store, to traverse, and support real-time applications built on top of that. So they're really designed for that high performance, those ACID transactions, the agility to change the model or morph the model as you're going along without disrupting service within that's of the application that's using the graph. That's a really key kind of item. And the graph itself, because oftentimes you don't necessarily need every information on every single log from historically 10 years of operation. You might only need the anomalous data points, so you don't necessarily have to store as much data in the graph as you might think. And the graph itself is optimized to be very, very efficient, as I showed you earlier, especially in the cases where you're performing a really high number of graph traversals. And lastly, as a developer, there's great productivity gains here. It's easy to learn, hard to master, as I mentioned, so you might want to investigate ourselves or the network of Neo4j experts out there. There's an increasing library of procedures and functions that are operating on within the Neo4j graph. There's a worldwide developer network that has those skills, and backed by our delivery on ideal roadmap and customer service driven roadmaps. So let's look at a couple of case studies and where these things are really happening, and why did I assemble this presentation kind of in this manner. So we have one of our larger customers is Telenor. They're a Nordic telecom provider, and they're delivering online, as it reads, mission critical self-service system to let users manage their privileges against their Telenor subscription. And what they were finding was, as their user base grew, they were having a difficult time handling that overall transaction, and where they would update their user environments and say, okay, a user's changed their subscription level, perhaps they're adding data to a data plan, where that update for the user to see would take a batch exercise that started to grow into daily operating hours. So a user made a change at 4 o'clock in the afternoon, and when they logged back in at 8 o'clock in the morning, the change might not have been taken place yet, which was frustrating for the user. It's a bad service level to be providing them. So in inserting the Neo4j graph, they and the authentication model there is operated by the graph. The processing time for any addition or change to their subscription level was processed nearly in real time and made the customers much happier, made Telnor look like it was a much more responsive vendor, and really helped eliminate or mitigate customer retention risks in this particular situation. Another customer is SFR Communications. They're a French-based telco company. They partner with Vodafone and are part of the Vivendi group. Their issue was overall the network management and IT situation. So they were managing the overall network, but they didn't understand what the impact was going to be in the event of outages. So they created a graph to tell them exactly what that impact was going to be. And as we demonstrated in our earlier network events, we talk about being proactive and identifying situations where you might affect a customer and notify them appropriately and early on, so they know what to expect, as well as the reactive model of there is an outage down, and how do you handle that activity and then bring either reroute traffic or bring that system back online. So the SFR situation, they found that having the inventory management capabilities to model their environment, to aggregate the activity on the environment, and have that single visibility of their entire network was really beneficial, and very, very easy to add new elements, new switches, new fiber lines, new new services into their environment was really important to them. And a graph schema changes really easily, or adapts to change very, very easily there. Another network and IT operations use case is Hewlett-Packard. They're a systems provider to telcos in this particular situation. So they're delivering the unified correlation analyzer, which is an overall systems monitoring tool that is evaluating activity on the network topology. So they wanted to accelerate the speed of handling alarm tickets. They wanted to automate that processing in many, many cases, and they wanted to eliminate the redundancy of, in the case of an outage, they kept getting told over and over and over again that the same device was out. Well, you only need to be told once that that's the case before, and you don't want to overwhelm the service providers, the individuals who are watching the system, with redundant information. So they needed that topological speed that the Neo4j environment offered. They wanted carrier-grade reliability within their cluster, and their benefit was they enjoyed new operations within 6 months timing of when they began the project. So really fast delivery here. My Communications is a service provider in Hong Kong, and they are the exclusive mobile partner for China Mobile. And so what their application is doing is helping manage both the social and mobile communications. So the relationships between different users, their locations, what that relationship happens to be, and what kind of services they can provide, like this photograph sharing example that we're showing in the picture. 3 million users with 200 million graph nodes on that in that environment, and allows them to communicate via voice, text, picture, etc. So they need that transaction speed. They need the ability to continuously update the graph itself for relationships, for new contacts, for friend suggestion, etc. And the graph delivered that kind of capability really effectively. Trey operates in the Nordics and in the UK as well, and they're trying to create a real-time customer profiling application. So their requirements were changing very frequently as they gained customers. Queries were difficult to execute, so they were having that join bomb problem that I alluded to earlier. So what they really wanted and what they achieved with Neo4j was these customer-facing applications were both operating very effectively in a cluster, so they were speedy. They were much more insightful in terms of what Trey could identify out of that environment, and they were much more responsive. So as they were adding in new features and as they were making changes to that particular graph, perhaps adding new services, really easy for them to do in the in this master data management style of use case. Global is another French service provider that's providing video communications, and their core was also to store and maintain the social network of callers and who they call, and help them connect with each other. So they were finding query complexity to be a big issue, and in adopting Neo, we were able to create both a real-time and real-time responsiveness, and help them evolve their social graph application to be very, very effective in helping their subscribers maintain better relationships with each other. And finally, I think I've got Cisco here, who is a device provider to to big telco. And what they were doing is they were trying to create a graph-based searching application so that their sales team could actually find the right literature to, for their particular sets of devices. And they have so many devices that identifying which was appropriate for each type of customer or each type of network expansion that was going on would oftentimes take them either weeks to seconds or minutes by creating this intelligent document query service or collateral query service using the Neo4j graph. They have another use case where their sales compensation application also had similar problems where their relational database was falling down due to the overall complexity of their comp plans. And of course, sales reps want to know what their commission is going to be at any given time as they're packaging and building out their different selling packages. So this hierarchy management platform made sales reps' understanding of what their commission payment was going to be much easier, and the graph was made it flexible. It made it flexible from the standpoint of changing the pricing models, from changing the compensation plans, or of course from changing the the individuals themselves, whether it's their sales territories, their particular role in the organization, or adding in new employees, replacement hires, etc. A third use case at Cisco is call center volumes and real-time recommendations for that call center service provider. And this is a really common one that we find of helping when a customer identifies that they're having a particular problem with a particular service. The recommendation engine behind the scenes is steering the service provider or the call center operator to respond in appropriate ways. And because you can't anticipate what the customer's problem is going to be until you're actually talking to them, this has to be an application that operates in real time. So navigating a knowledge base, understanding and identifying that when the customer is mentioning particular keywords, using perhaps a listening device or that's processing their communications using NLP technology. That activity is then going and searching the knowledge base, identifying possible situations or remedies for that situation, and then delivering it back to the customer support representative in real time. So this kind of delivering and improving customer service levels is a very, very highly motivating type of application for our telco customers right now. As we wind down, we'll look at what makes the Neo enterprise class in terms of its ability to scale, in terms of its ability to support large telco types of applications, which oftentimes are global in nature and are require massive scale. So the enterprise class product for that Neo offers is indeed binary hardened and tested, is indeed offers clustered replication, soon to be across data centers coming up in about 2 weeks. Is expected to intelligently manage its own, both storage and memory. You will use all of its available hardware resource. That's what Enterprise Lock Manager means. And other capabilities like offering the network admin monitoring tools, offering the network admin monitoring APIs that allows them to build their own custom kinds of tools above it, or supporting specific enterprise schema requirements. Perhaps there's regulatory requirements that must be met, and therefore data that meets those requirements must be captured in the system. We have the ability to do so. And all of that is surrounded by the overall innovation network of Neo4j. That includes the contribution network of the open source community. That includes the technology partner network, the OEM network that we have, like I've just mentioned, HP, the growing service provider network of folks who have put in their 10,000 hours and are able to help build a graph effectively. In fact, we have a video of an interview with another customer of ours from Orange, another European telco provider, and their lesson learned was you have to take time to evolve your graph, because the more you evolve your graph, the better you get at building a graph, and your data model improves over and over again, and therefore your applications themselves improve in a likewise manner. So we're kind of adopting the ideas around Metcalfe's law of the network, where the value of your network increases with the number of nodes you have within it. We believe that the Neo4j network operates in exactly the same way. We're seeing graphs being used as a launchpad for all kinds of brand new technology, technologic innovation, whether it's artificial intelligence, natural language processing, additional machine learning capabilities, advanced predictive analytics, and Internet of Things activity, connecting the physical devices to in the digital space, and then to business processes. That's going to be another huge opportunity for graph to really help that part of the industry shine. We're seeing right now proof in the world, in both nature, in science, and in society, that the denser the network within which you operate, the more innovation that happens, and the speed at which that innovation happens is much faster than sparse networks. So this law of dense networks is something that we're exploring as a vehicle to really illustrate the value of being a commercial customer of Neo4j's. So you can identify what that next adjacent possibility is going to be. And as I mentioned, right, graphs are easy to understand and learn, that whiteboard model, but they're still hard to master. So it still requires the investment of experience and the investment of time, whereas we're allowing you to operate in this connected enterprise kind of model, where the innovation acceleration, the expertise in graph, and the Neo4j graph database platform itself, all of those combine to make the network within which Neo4j is operating of really high value, especially when your applications require global scale, they require real-time performance, and they require the kinds of innovation that we've been discussing. So for more information on all of this stuff that I've just talked about, please visit a couple of locations. One of my favorites right now is our new Neo4j sandbox. That is an instance of Neo4j in the cloud, preloaded with particular use cases. If you're interested in the American election, we have one that is tracking the BuzzFeed information that we call Trump World. We have congressional information in another use case. We have our recommendation engine that is evaluating a movie database, and we have our Twitter information that if you want to evaluate what your social network looks like. So the sandbox is a really good vehicle to just try out and see what the graph looks like, see what the Cypher language looks like as the programming language, and see what a graph, visualize what your graph might be. And then on the other side is the use cases that we've got that I've just covered. We have really deep content in every single one of these use cases, whether it's security control, fraud detection as we walk through, network and IT management, master data management. All of those are available in our resources section.